So you have seen the difference between 2 and 4 layer PCB, which was quite extensive, as shown here. So the 2-layer PCB was just a trial to see whether we can do it, and we could do it. Actually, it was working perfectly. The problem was EMC, and we could not achieve the EMC regulations, could not reach them. So we had to go to 4 layers, and the difference was very obvious. Now, how would you go to a multi-layer PCB? How to choose the layers? What type of layers? What arrangement? This is quite a big question. First of all, we have to ask ourselves about technology, whether we can make such a PCBs. What is the production yield? What is the reliability, a long-time reliability of the PCBs? So this all affects how we design and choose what the layers are used for. The EMI, the radiative EMI and conductive EMI, that all is very affected by the choice of the layers. What are the layers for, each of them? And what to use them, whether we use planes or ground planes, power planes, how many? How is the coupling within the circuit from one track to another, from one signal to another, from power to ground, from power to signals to power? And how the PCB operates, how stable is the power supply voltage, and about the signal integrity of all the high-speed tracks, such as, for example, the impedances of the tracks and all that. So let us go now through these criteria. The first criterion is, of course, what would be the thickness of the layers? Because the PCBs are made by using 2-layer basic PCBs, which have core in the middle, and then adding prepregs and copper sheets and then press them together, as you all know. Till now, I hope at least you remember the lecture. Otherwise, you check out back. So that's the main core. So this is the core, and this is the prepreg. And here is the prepreg as well. The core has different properties than prepregs. They have different relative permittivities. They are not the same. And they have different thicknesses. And the copper layers are also different. Usually the inner copper layers are 17 microns and the outer are 35. So all that should be kept in mind. What else? If you have a highly unsymmetrical stack, for example, we have one big ground plane and then no ground planes anywhere else, the PCB can bend during the production. So you have an uneven bended PCB. And the other thing is, if you have multiple stack PCB, multiple layer PCB, and there will be a lot of copper on one side and less on the other, when you press it, the thickness would be uneven. So you would have some valleys in your PCB, which would then also cause production problems. So you should try to keep amount of copper and the stack of the PCB as even and symmetrical as possible. So if you have a ground plane on bottom, you should also have it on top, at least to some extent. Please try to keep the symmetry so that the PCBs wouldn't bend. The wire types, of course, you all know that through-hole wires are of course okay. Then you can make micro wires. These are also okay. These are buried wires which are quite expensive. Please avoid them if possible. And these are no-go wires because actually that would be enormously expensive to make a wire that doesn't go within the core. That wire till here is a part of the core which can be made separately. Then you put a prepreg and then you press. How would you then make this wire? It's impossible. You cannot make it. You cannot drill to a certain distance otherwise than using a stack of micro wires one on top of each other. So this is, please avoid if possible. Well, you can make such a wires if you use so-called back drill technology. What's that? You can make such a wire by making a through-hole wire and then drill from top and bottom to a certain depth and make a hole without that wire. So that would make a wire just between these two layers, but it would still leave a hole on top and bottom. And here, back drilling from here or there would make wires between these layers, but that would be done after the production, at the end of the production. What about EMI and operation criteria? The power supply energy. The energy that comes to power supply the circuits comes from the dielectric between the planes. You all know that you have initially, of course, bypass capacitors. The bypass capacitors have a certain inductance. And that inductance, as you all know now, comes from the size of the capacitor and also comes from the track length. So you cannot make it smaller than to a certain extent. Which means that for the highest frequencies, I'm talking about gigahertz now, you cannot achieve a good powering without a nice big ground plane just below the nice big power plane. So the ground plane and power plane are here now forming a capacitance of the highest possible quality. And all the power that comes from that capacitance at high frequencies would then power the chip. So no power at these high frequencies would come from capacitors whatsoever, because they would just not work at these frequencies anymore. So please keep in mind that power and ground layers or continuous layers should be kept together as close as possible to maximize the capacitance of these two layers, and that would deliver the highest quality power to the microcontroller and to the digital circuitry. What about high-speed return currents? For high-speed return currents, you want the tracks to be as close as possible to the ground planes. So just the opposite. Now the ground planes, these are two ground planes now, should be as close as possible to the tracks. And that would make the smallest current loops possible. Okay? Line impedances. In order to achieve certain line impedances and the differential line impedances as well, you should have a certain thickness here. And for 50 ohm impedances, you have seen that to make a nice narrow tracks, you have to make really narrow thickness of the coppers, below the copper of the dielectric, which means also in favor of this design, so that the power planes and ground planes are very close to the tracks. I'm talking especially ground planes, of course. What else? The power supply noise. If you have a power and ground plane like that, then the noise within this capacitor that is formed by it is then transferred to tracks. And if these tracks are next to each other, like here, one has field towards this, let's say ground plane, the other has also field towards this ground plane. So again, you have a lot of cross coupling, noise coupling from that track to that track. You have noise coupling for this power plane to that track and that track. So all of the noise that is present, and please assure me that there is a lot of noise present within this capacitor between power and ground plane, all that is then coupled to the tracks. So you should avoid that. What else? The EMI shielding. If you have a power and ground plane on top and bottom, or you have two ground planes, whatsoever, there is a nice shielding outside then, because these tracks have this noise, and this then acts as a nice big shield around them. So all that noise would be then kept within this stack, this sandwich of two grounds, or power and ground, because this nice big copper area acts as a shield between the tracks on the outside. So for EMI shielding, it's better to keep high frequency tracks within the layers. What else? Crosstalk. the crosstalk between tracks can be minimized by shielding. For example, this is a ground plane, this is a power plane, let's say. So the noise from this track is then, or the signal of that track or the energy of that track is kept within this area here, and that one here, and that one here, and that one here. So this ground plane acts as a nice shield to minimize the cross coupling of the noise between the tracks. But also, if you interleave this track, so one is here, the other is interleaved, then you have a nice separation of the return current as well. And this separation of the return current also minimizes the crosstalk. Even more, you can minimize the crosstalk by orientation. For example, this is a ground plane. All the tracks go in that direction here, but the bottom tracks go in that direction. So the orientation of the tracks also greatly minimizes the noise coupling. Or maybe I will now delete those, and let me put the ground track here and ground track here. Plane. These are two ground planes. Now, if these tracks go in horizontal direction and these go in vertical, then you have again minimized the noise coupling between these tracks. And finally, the high-speed signal changing. If you have a high-speed signal that comes on the upper track, changes layers, and continues on bottom track, you have to provide the change of the return current as well, because the return current would actually turn on top of that track, on that ground plane. These are two ground planes. And then you would have to provide a via, and then it would continue in this direction. So the return current also changes layers, but only if you change two layers. If you just change one layer, then the return current would flow on the same layer because it would be a continuous ground layer. This is shown actually here a little bit more in detail. That this is a signal in forward direction, changing two layers, and the return current flows on the bottom side of the copper, then changes to top side, goes through the wire, goes on bottom, changes to top side, goes around and returns back. So you have to provide a wire for this return current as well. Well, if you just change one layer only, then the return current has no problems returning from bottom to top layer and way back. The wires themselves also are quite nasty because they have quite high inductance, a few nanohenries. But if you look from the sides through the PCB, what do you see? You see big, unshielded plane of wires. And that noise of that wire is coupling very, very far away because it does not have any shielding around. There is no copper surrounding it. It's just a single pillar, and it radiates a lot of noise all around this group of pillars of wires. So avoid these wires in high frequency conduction paths if possible. If not possible, well, you can make a shielding wires around. Here you change the layers of this USB, you put a few wires around, and then these shielding wires then act as a shield. So that's the signal, changing layers, the high-speed signal. This is a two differential signal, so there are two, and this is the shielding wire. That's one, that one, and that one. Around, making a nice shield around this initial wire. So let me go now to show you the different PCB stacks you can have in your design, starting with 4-layer PCB. This is a 4-layer PCB example. We have a ground plane, we have a power plane, we have two signal layers. What is the advantage of this PCB? Well, it has a very good connection between ground and power, a nice capacitor between ground and power. If you have components on top, then you can connect them easily by signal layers on top. If you want to connect to ground, you put a wire here and you put a wire there for power. Of course, these wires are all through-hole wires. And the only actual problem of that stack is that it has quite a large distance between the ground plane. So where would you put the highest frequency signals here? Of course, you want to put them where they are closest to the ground. So here I would say on signal layer 1, you would put the high frequency signals. Here you would put low frequency signals because they are further away from ground. The distance between ground and power plane is determined by the capacitances. The smaller it is, the better. But to be frank, such a 4-layer PCB stack is almost never used. Why? Well, because there is very thin prepreg here. Sorry, that's not a prepreg, core. Having PCBs with very thin core is hard to maintain or hard to make. And then you have a lot of prepregs up and down to make final thickness. For example, if you have 1.6 millimeter board, then you have maybe 0.2, 0.6, 0.6. That would be something in that range. So you need at least 3 prepregs there, 3 prepregs there, and then you make a stack. And the biggest disadvantage, not just manufacturability, but the biggest disadvantage is that you cannot get required impedances of lines because that thickness is just too large. So you cannot, if you want a 50 ohm line, then you would have to make it very wide. And in terms of EMC, of course, we would rather have shorter distance between the track and the return ground plane for minimizing the ground loops. So that PCB is not recommendable, actually. The most common PCB, 4-layer PCB, is like that. So it has short distance between the layer S1. So this one is intended for high frequencies. There is ground just next to it. The capacitance between ground and power plane is, let's say, moderate, not the best. But you can make lines with nice, narrow lines with low impedance. Low frequency signals are on bottom layer. And, well, that's more or less it. If you want make a 4-layer PCB that has, how to say, even lower EMC footprint, you can make a layer PCB like that. So you have ground plane on top and power plane on bottom, and then you have signals in between in a sandwich, just the opposite. Well, in this case, the ICs on top cannot be connected directly between each other. The components on top have to be connected via wires. So you need a lot of wires, which is a disadvantage. But your high-speed signals are now contained within the sandwich, which is good. But all the high-speed signals and the low-speed signals here, so here again high-speed signals, low-speed signals, are within the sandwich which contains high-frequency noise from the power supply. So it's not a good idea as well. Even though for the EMC probably it would work better than that one. What else? Well, you can combine the layers. You can say, okay, I would like to have really good ground planes, but then the power would be combined. So if you have the most problems with the EMC, then you could go with the following arrangement. You have 2 ground layers on top and bottom. And then you have combined power and signal layers on both sides. So now both layers are good for high frequency signals. They both contain power planes, so you have a nice capacitance here, and this noise is not coupled to the rest of the tracks. And one thing which is really as well important is that when you put a component on top, you can connect it to this power plane and ground plane with very, very short connections. Here, of course, you need a through-hole wire, but you can also use micro wires. But what is important is that this track lengths without wires on one side and with very short wire on the other would make the best connection of these high-quality capacitors to these ICs. And the last and the best there is would be using ground plane on top and bottom, having ICs there, and then of course you need wires for every single pin connecting, but you have really good capacitances there, you have very well defined impedances of these tracks, very low current loops, very good shielding, and I would say among all these 5 to make a verdict, that one is never used. This one is quite often used. I would say the most common. The most common. And that one would be the best there is in terms of EMC. And also, even though you have to use wires to connect every single pin of your devices on top, you still have a lot of space below to connect tracks, because there is no interference of the ICs. No pads are on your way. So you can make really dense tracks going all around in the mid layers. And then you have top and bottom plane shielding everything from the rest. So if you have EMC problem, this is a go. If you just need a quick solution which does not have a lot of EMC issues, I would prefer that one. Why would that one be preferred? Well, because you don't need a lot of wires to connect the ICs, because they can be connected on top layer as well, and of course the bottom and so on. And maybe then I would go and use the rest of the surface for power and ground. So mostly I would rather see that you have 2 ground planes and you use the rest of the surface for power than having 1 ground and power layer dedicated because of this capacitance. That capacitance is probably lower than this here if you just you're able to supply as many areas for power. That's a typical PCB stack. Actually, 2 PCB stacks are often by this cheap producer, and one is with 0.2 millimeter prepregs and the other is with 0.1 millimeter prepregs, and they all stack up together to 1.50 something millimeter PCB. So these are 2 PCB stacks you can order. Actually, there are many others, but this is an example of the cheapest supplier. Let me show an example of a 4-layer design. This is a 4-layer design using Raspberry Pi Zero and some LVDS video connection. This is HDMI. These are USB 2.0. These are SD cards, and Ethernet is below. So nevertheless, these are the tracks, high-speed differential tracks. These are single-ended tracks. And all of that is then done in a 4-layer PCB. So this is the top layer. That's the first middle layer, which is totally ground. Everything is ground. The next layer is also ground, except some of the power planes here, here, here. And the grounds are connected together with wires. As many wires as you can see are all ground wires, many wires actually of these. And finally, the bottom layer connections, and the rest is again ground. So there are many ground planes, even though the layer is dedicated for signals, there are ground planes anywhere possible. That's good in several ways. First of all, with a lot of ground planes and connecting them to each other, you make a really nice and firm ground plane that has the lowest possible impedance, which of course would decrease the common mode interference problems. And you make even PCBs. All the layers of the PCB are covered with copper, And so your thickness is even, and also there is no bending because of no asymmetrical issues. And of course, finally, which is quite obvious, that return currents are possible for every of these high frequency lines just below them back to the source, because they contain a high frequency, they contain uninterrupted ground plane. So let me show you this uninterrupted ground plane a little bit more in detail. So that's the signal, let's say that one here. You see all these 4 differential signals have uninterrupted ground plane below. All these there as well, these red ones here. But there is on this ground plane, there is a power supply going down here. But under this, over that power supply track, there are no high frequency tracks available. So good. What else? The bottom layer, you see 2 high speed tracks here and here. So let me show you one about that. Here is a continuous ground plane now on bottom, on the mid layer M2, and here as well. So these now have ground plane just above these tracks. And again, they can provide a return path very easily. Let's go to 6 layers now. The simplest 6 layer will be that. And you already see what is wrong with it, I hope. Because the only good thing about this 6 layer PCB is the capacitor here, which is a very nice capacitance between ground and power. But all the rest is crap, because actually the distances are too large. So your loop sizes do not minimize as much as they could. The impedances of the tracks could not be achieved small enough for the required impedances with the width which would actually be usable. And the layer 1 and 3 and 4 are for low frequency signals only. The only layer which is acceptable for high speed signals would be layer 2. So this is almost not used. Well, let me go further. What about that one? Well, that one has another problem, as you might see. The high frequency signals would go here, which is quite okay. But all the rest are, maybe that one, the layer 2, would be even for very high frequency signals, because it's shielded within the shield, right? But these 2 are just normal layers for low speed signals. But the problem here is that there are 2 tracks within the sandwich, ground and power, and all the noise from ground or power would actually be coupled to them. So you should not put any noisy, any sensitive signals inside here, because the noise would just couple to them. And that noise would then spread all around. So this is also not a good way of making 4-layer, 6-layer PCBs. Well, if you have enough to spare for a little bit more, you can go for that arrangement when you have two ground layers, which is quite a good option, because you have now the power layer very close to ground. The ICs on top would be connected to it with very short wires, so that means also low inductance to the ICs. The power would be very good at high frequencies with low impedance. The tracks on top are for all the tracks can now be used for high frequency signal. High frequency, even here very high, because that one is contained within the sandwich, and here you can route the most high frequency signals. So that arrangement is quite good, but then what you have is, of course, only 1, 2, 3 signal layers, not 4. Maybe you should also take care that these go left and right, and these are back and forth, so that they do not cross couple too much. Maybe you should interleave the signals. What else? Well, you can make such a sandwich. That one is even better. But that one, of course, has only 2 layers now. 1, 2. Didn't we have that already in 4-layer PCB, right? But that one, of course, has a main advantages. Yes, you have still only 2 layers, but you have the best power possible. You have the ground reference, you have the ground reference here. Now, the only problem is that if the IC is put on top, besides of course the problem of the thickness of the layers, is that now the wires are a little bit longer to power and ground. Actually, the wires go all through, right? So this is the connection point of the ground. And this is the highest frequency signal coming from, highest frequency power supply current would come from this then, which is a little bit longer than here. So among all those four, I would say that one is certainly the best option for 6-layer PCB stack if you want to have how to say, medium density tracks but high quality power. Now the problem of that stack also is that this is the core, that's the core, and this is the prepreg. So the prepreg is thicker, so you have to have several layers of prepregs, and you have to deal in production with very thin cores, which would maybe cause some issues. Depends on the producer. Here the cores are thicker, this one and this one, and the prepreg is thinner, which would be a more acceptable production. So what else we can do with 6-layer PCB stacks? Well, let's go even further. Let's do something like that. So what do we have? We have ground and power together, which is good for power supply. They are close to the IC, so the ICs on top are connected directly to them. What else? We have another ground plane here, so all high-speed signals would be here and here. Here would be the low-speed signals. Sorry, layer 2 would be high-speed signals. And the direction here may be left and forth, here back and forth, so that to minimize the cross-coupling. But we can use the unused layers for ground and power. And now we have even better PCB, because all the unused areas should be used for power and ground in a way that they are interleaving. So you should use power layers here and ground there, because now these tracks are now confined within these two ground layers. This provides another capacitance, and here as well. And there are no tracks between the power plane and ground plane, which would be very beneficial for noise coupling from power to the tracks. What else? That's another option. From the first glance, that one doesn't look very good because the power and ground are actually very far away. But if you put another layers of ground and power on the unused areas, you can actually get a nice coupling between power and ground, and here between ground and power. And almost by placing the planes in the way, you would prevent this capacitor to happen at all, because you don't want this capacitor to form, because that capacitor in between here would then cause the noise coupling to these lines, to these tracks. So you put ground planes and power planes in a way that it doesn't interfere with the tracks within. And that allows you having 4 signal layers instead of 3, but unused areas should be used for ground and power. And the high-speed signals should then be taken on layer 3 and layer 4. So maybe it's better to put components here, high-speed components. Well, by turning this PCB upside down, you would get it normally. What else? This is another option. What is that thing? Well, you have signal ground, signal ground, signal ground. That would be the best for some, I would say, very sensitive circuits, or where the cross coupling is your main issue. So you want to minimize the cross coupling between that one, and that one. So all three signal layers now have a defined ground below, and they do not have almost none cross coupling because of the distances as well. This is the core, and this is the core layer, which is thicker. So you have to provide some power, and of course you do it by providing, whenever is possible, you provide power layers on all signal layers. And then you have nice capacitances between power and ground. And finally, that's the last option, 4 signal layers, 2 ground planes, very similar to those, and of course again putting power and ground planes, power planes whenever there is option, and interleaving. So there is never put tracks within the sandwich of ground and power plane. So the choice among those stacks, it depends on the type of the circuit you're working on, and of course the density of the tracks. If you require a high density of tracks, you have to go with more signal layers, but never avoid ground planes. So to summarize here, I would say use at least 2 ground planes, at least 2. All the rest can be a combination of tracks and power planes. Maximize the areas of power planes with respect to the closest ground so that you maximize the capacitance, and interleave in the sense that there is no meaning putting ground plane here or here because there is already there. So rather put power plane there, and you would have increased the capacitance of your power supply. And here, for example, there is also this capacitance. Not the best there is, but you can maybe utilize it if you want. So that would be advice, or the summary of that 6-layer PCB stack, or any PCB stack whatsoever, more or less. Because these options there, at the beginning, this here, when you have the whole layer for power plane, it's not usually very good, except when you have layers of ground and power very close together. But probably it's better option to use a combination of ground planes like here. That you have continuous ground planes, and then you add power areas whenever you can on the signal layers. This is an example of a 6-layer PCB stack from JLC PCB, the only one they offer for the price. So 0.1 millimeter, 0.5, 0.1, 0.5, 0.1, roughly. So what kind of stack you would use here? Well, it's up to you, but I would certainly go for 2 ground planes, and then I would use the rest for power and signals. Price comparison. Well, as you see, at low quantities, you have prices very different. But when you go to large quantities, you see that for 2-layer PCB, it even doesn't change a lot, because for 10 pieces, it's a budget price they are giving for to get the attention. But as you see, for higher volumes, there is almost no difference. But for 4-layer, you see the price drops quite a lot, and for 6-layer, even more. So when you go for large quantities, you see that the prices do not change that much, are not that different. Between 2 and 4-layer is maybe a factor of 50%, a little bit more, 100% for 2 to 6-layer. But it's still in range of dollars per piece. These are prices of course for the basic stacks, and without any special wires, just through hole wires. Let's go now to 8-layer stack. In 8 layers, this is a no-go. You already know why, I suppose. everything is wrong here. The distances to the planes, the plane and ground, they are not close together and there are tracks in between. Well, you can go to that option. That would be a better option. You have power and ground, you have ground on top and bottom, and you have 4 signal layers. All signal layers are for high frequency signals, especially signal layer 2 and signal layer 3, because they are close to ground and they are within the sandwich, and power and ground are also close together. And the prepregs, which are lighter, are here a little bit wider, so you need maybe 2 layers of prepregs or 3, depends on the total thickness required of the PCB. So the signals should be interleaved, or maybe different orientations to minimize the cross coupling. Maybe the only problem is here if you want to change layers. For example, if you want to change layer from here, from that signal to that, it's not a problem because the return current goes on the same ground plane. If you want to change layers from here to here, then you have to also change the ground plane reference. So you need to put a wire to connect these 2 grounds together. What else? For powering the IC on top, the wires are quite long from here and from here. So that would increase the inductance of the wires. So maybe it's better to use this option, because there you have a power and ground layer close to the ICs. So if you have ICs on top and maybe on bottom, this could be an option, because then you have close connection of both. But high-speed signals would then be routed here and here, very high, and here we would have low speed and low speed. Why? Because there is no ground plane close. The capacitance is very large, the noise does not couple to other layers. So it's quite a good stack. The only problem of that stack actually is that for each high-speed signal you have to go within. So if you have a moderate number of high-speed signals and all the rest is low speed, this might be an option. What about that one? Well, that one has ground on top and bottom. Well, that's very good because everything is in the stack. But the power plane is very low below. So there is a capacitor between ground and power which also contains all these tracks. So there is noise coupling to them, which is not a good thing. The highest speed, very high, of the signals should be here. Maybe also there. But there all the noise is coupled within here, because here is also the capacitance. So this is not a very good option. That one is good. That one I would say it's very good. That one is okay. That one is no-go. And that one is, well, questionable. So maybe I should go further to other stacks. Okay, before I go to other stacks, just one thing more. Here, I can add some planes, and now the story changes. Because now, if I add another planes on layer 2 and layer 3, I might improve the situation. Because now if I put them interleaved in the way that the capacitances here do not interfere with the rest of the tracks, then I might get a much better option. So that would maybe be then a good PCB. But only if I really utilize the ground and power planes in the mid layer. Alright, what else? Typical PCB 8 layer is shown here. It is a here. It is a motherboard. I cutted it and I polished the edge. So you see it's an 1, 2, 3, 4, 5, 6, 7, 8 layer PCB. And these are differential connections on top, and there are some on bottom, and there is ground plane, ground, power. So the stack is as following. This is the wire, it's a through hole wire for this resistor. And this is a close-up. So these are differential lines. See, they are interleaved. They are not one on top of each other. These, for example, these are already interleaved. So we have signal, ground, signal, 2. Then we have power, ground, ground, power or ground, signal, signal 3. We have ground and signal 4. So at 8-layer PCB, we have 4 layers of signals. We have at least 3 ground layers and 1 or 2 power. Depends what type of what thing is here. Because as you see here, this is not all over. See, it finishes there. This one starts here and then goes further. So it's not completely ground plane or power plane, but it's interleaving. Whatever we want power, it's power. The rest is ground. And these are the thicknesses. So the core is here, here is the core, and here is the core, and there are prepregs in between. So you make one PCB, another, you make three main PCBs, then you add prepregs, you press all together, and then you drill holes, and you start with metallization process. What else? We have a 10-layer PCB stack. In 10 layers, I would already start with that one. Okay, higher speed signals, very high speed signals, I would put them here because they are close to both grounds. The capacitance between ground and power is quite okay. Then we have 2 layers of signals there and there, which are low speed signals. Well, a lot of low speed signals. Do we need them so many? Well, probably not. Depends. Maybe this would be a good option in case when you have not so many high-speed signals. But if you have them, then you have to use more ground planes, at least 3. Well, 3 ground planes would mean then you have high-speed signals here, very high here, very high here. Please note here we have to use interleaving or different orientations to minimize the coupling. Here is a nice capacitor. Then we have low speed signals there, and then we have again very high and high speed signals there. So a lot of high speed signals, but the power bypassing is not that good because we have only one single pair of power and ground layers. So maybe we can improve that by adding some extra, and that would be then a better option. And please note the interleaving again. Capacitance, capacitance, capacitance. Additional ground and power layers. Okay, that's another option when we just put the high-speed signals within. So now we have very high-speed signals all there, here, very high there, and let's say low speed on layer 5. Because here the tracks are close to the power plane. Now there is only one capacitor between ground and power. The problem is that this IC is there, or maybe here, would have a little bit longer wires towards the power plane. Of course, the wires towards ground plane as well, because that one provides the high frequency power. So again, it would be very beneficial if we added some extra ground and power layers. But that PCB arrangement has a lot of very high speed signal layers, like that one as well. And it has ground on top and bottom, which is beneficial in terms of the shielding. So for EMC, that one would be probably better. And finally, this one. Power, ground, ground, ground. 3 ground layers, 1 power layer. A problem is here. High speed, very high, very high, very high, very high. 4 layers for very high speed signals, 2 layers, 1 for high speed signals and 1 for low speed signals. Now, adding extra ground planes and power planes would make it better in terms of power supply, because that is then increasing the capacitances. And of course, you put the planes in the way because they are not the same. Power supplies, there are many. So you choose the planes in the way that you supply the power to the ICs on the same side. So this power plane would probably supply the power for top ICs, this one and this one to bottom ICs if they have more of them. Okay, 12-layer PCB stack, wow. The 12-layer PCB stack, which would be quite okay, is probably that one. If you need a lot of high-speed layers, high speed, very high, very high, very high, very high, high. So all are high-speed layers, which are the ones which are within the stack are the highest speed layers. We have only one pair of grounds and power. But that's a good stack because if you can utilize all the rest of the layers for power supply, whenever there is a space. And there are spaces there, you may imagine. Let me show you another stack which is also very good, because now the power supply and ground are close to the top and to the bottom layer, which means it's very beneficial for top layer and bottom layer components. And then you have one ground still here and here. So now we have high speed, very high, very high, very high, very high, high. Again, the same as here, but a little bit less ground planes, and some of them are used for power. So this would be even better in terms of the power supply bypassing. But adding extra ground and power supply layers wouldn't hurt. And finally, I would like to show you an example of a 16-layer board. It's actually a demo board for Altium, from Altium. It's a microprocessor board with some very fast connections. The microprocessor, the DDR RAM, the DDR on the RAM in the SODIMM, the PCI Express, the Ethernet, the USB connections, display port, and some optical connections as well. So all of that is made on a 16-layer board. So what was the used stack here? The used stack was actually that one. So we had top layer, high-speed signals, connection, capacitance between ground and power, another ground layer, another capacitance. Then we had very high-speed signal layer, we had low-speed signal layer here, we had very high-speed signal layer, very high-speed signal layer here, high-speed signal layer there. So all are very high or high except that one. But I will show you what's happened with the layer 3. We'll quickly see. So there are power planes there. Again, we have a ground plane. Capacitance here, we have capacitance here and capacitance there. So close to the ICs on top and ICs on bottom, we have ground and power layer. So we have a close connection, very short connection to these ICs. All the wires are through-hole wires, so no micro wires are used. So this is how it looks then if you have a wire that connects power layer with the IC. So you see how low it goes down to the bottom, but it connects power layer with top layer S1. All the rest is unconnected. This is for power supply, and this is the ground wire. It connects all the grounds together. And as you see on each layer, we have a ground actually. Also on those which are maybe just used partially for power. You will see that. That's the example of that PCB. And what do we have here? We have the USB 3.0 connection in that direction. We have the Ethernet, 3 Ethernets there. We have the memory connection there, memory connection here. We have the PCI Express differential lines there, and we have the mini PCI Express connector there. So high-speed communications also here. So all the PCI Express connections are made on top. Why? Because they are differential lines, and differential lines tend to cause much lower noise. So they are put on top line or top layer. The lines are actually changing voltage differentially, and from far away that is much less influencing the noise. So these lines are on top. There are lines also for USB 3.0 here, and that's it. These are also differential lines. Now let's go. Display port is also there. These are display lines, display connection lines. Let's go to signal layer 2. Signal layer 2 is actually on layer 1, 2, 3, 4, 5. Here. That's signal layer 2. Now we have connections to the memory, the DDR memory here and there, and also Ethernet, one Ethernet. But not also that, we have a lot of ground planes around, and some maybe also, or there are also some shields connecting, shielded connections. What else? Layer S3. Layer S3 is here between two power planes. This is so-called low-speed layer. Interesting. Also on the low-speed layer we have a lot of high-speed connections. What do we have in between? I will show you. But please remember that. Also on that low-speed layer we have high-speed connections. Let's go further. On layer S4, high-speed connections again. Layer S5, high-speed connection again. Layer S6, that's the bottom layer. These are again these differential lines going to the PCI Express. And as you might see, all the layers actually are poured with ground. Now, power supplies, layer 3 power supplies. You see many power supplies are routed around. Many different voltages are required for this IC, and the big planes are used for these power supplies. 1.8 volt. Now that one is just above that low speed signal layer, remember? And just above that low speed signal layer you see that only this part is used for power supply. All the rest is ground. So going back to this so-called low speed layer, you see that here, I think it is S3, yes, if I'm correct. S3 is the so-called low speed layer. Actually, grounds are used on top and bottom layer for the high speed signals. There. Here are the high-speed signals going. And there are also some here as well. You may remember on layer S3. All the high-speed go from here on. But there are some there as well. Where are they? They are crossing this area of the power supply. What else? Layer 8. That's the power supply of the VDD, that's the power supply of the DDR memory. Since this is the fastest ICs that are here with the fastest connection, this power supply is the largest. It has a big area between the plane and the ground. And final power supply layer is here. So to go back, each power supply area is as big as it could be, but the rest of the area is used for ground, especially where there are high-speed signals. So to continue, here is the detail of the microprocessor. So the top layer, you see these are the BGA pads, and each BGA pad has a wire next to it, and this wire goes down, and that wire then connects to a certain layer. And the colors here are representing the different pin functions. The greens are the power supplies of one kind. There are other purple power supply of other kind. This light blue are the grounds, and so on and so on. So all that have to be connected through these layers within. And on the bottom we have bypass capacitors. There are 4 different power supplies for this IC required, A, B, C and D, and these all are bypassed by this bypass capacitor. The smallest are the ceramic capacitor just below the pairs of ground and power supply, here, 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 here. And the big ones, which are the bulk capacitors providing the low frequency power to these high frequency bypasses, are here. Also the tantalum, the one which has a lower quality for resonance damping. And the highest frequency power is actually not taken from these capacitors. It is actually taken from the ground planes. And that would then make the capacitance the best there is. It's taken, sorry, it's not taken from the planes, it's taken from the space between the planes, between the ground and power planes, which are kept closer in this stack. Here, here, and here. And to finish, what you should learn from this lecture is, of course, that you are able to identify high frequency current loops and minimize them. You're using different techniques, such as ground gridding technique on 2-layer PCBs, or ground planes on 2 or more layer PCBs. You should be able to determine the transmission line dimensions using the appropriate software, such as Saturn PCB. You should be able to assess pros and cons of the layer stack which are shown to you, and then you can analyze them in terms of the producibility, the EMI, and the quality of operation, as I've shown you in this lecture. You should be able to select some for your design optimal layer stack according to the signals you have. And if I show you a PCB design, you should be able to identify a routing problem so you have to be able to follow the tracks, follow the return current path, and identify any problems with that. And here is an extensive list of literature I used to make this lecture. And if you have any problems, any issues, of course you can go through this list and check them out. And by finishing, what I can say, choosing an appropriate layer stack is a big task, which has to be done at the beginning. So you have to have quite a lot of experience to be able to choose it properly. And usually you look at the number of components you have, you look at the number of layers, number of signals which are critical, number of the interconnections as a whole, and then you choose the number of layers. And then you have to choose what are the layer properties, which of the layers will be used for ground, which will be used for power, signals, and so on. Whether you would use double layer placement of components or just on one side, whether we use through-hole wires or maybe micro wires. But then you can make the PCB and it actually works, so you're happy, but doesn't mean that it will actually go for the EMC. And a recipe how to make a PCB to be able to fulfill both is it's not a black magic, I would say. It's just not something you can do right for the first time, because you have to use the optimal, you have to use the optimal arrangement, not just the best there is, because you might not be able to afford it. because your boss will tell you, please, you have to keep the price low. So you have to go with the minimum affordable. And that's hard, because we all can take 16-layer PCB and it will be always great, almost. But you cannot afford it. Therefore, you should go with the least number of layers possible, and you should use them wisely. So I would suggest always, in the name of the EMI, use as many continuous ground planes as possible. Add power planes next to them and use the rest for high-speed signaling, especially those layers which are confined within ground planes. These are the best for highest speed signals. And then utilize all the area that's left for power planes, ground areas, and interconnect them as well as possible with wires. That would be a short recipe for your designs when you encounter such a challenge.